All right, the next portion of study deals with waves that combine with other waves. First of all, one thing that I want to mention is that typically musical instruments are not made up of pure musical tones. Usually, the waves produced, or the characteristic waves of a musical instrument, and if I draw them, let's just draw again I'll see if I still have it in memory, the closed tube, which sort of looks like that. You get the idea. And again, I'll just move that up, group this bad boy. Let's make it a little bit larger so we can draw better waves. Musical instruments, or the sounds produced by musical instruments, are not usually pure tones. We're going to end up with a composite of, or the combination of, let's say, the fundamental frequency, which would be a quarter of a wave. And then again, you'll get resonance at, let's try that again too. You'll get a resonance or music or sound at that frequency, 3 times the original value. And then finally, let's just pick a different color. You'll get resonance again at 5 times the original value, which is going to look something like, oh, I don't know that. And when you combine all of these tones together, you don't get pure sine waves. You get very unusual waveforms that look a lot like maybe EKGs. And the shape of these waveforms depend on the relative abundancy of each of these, what we call overtones. Those overtones being F, maybe 3F, 5F, 7F, and yada 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 to the F, to the nth F, whole numbers, odds in the case of a open at one end, closed at one end. And all of these different frequencies will occur at different volumes, and this will give our musical instruments their characteristic voices. So a clarinet will sound a lot different than a violin, will sound a lot different than a piano string that's been struck. If you look, the predominant frequency for a clarinet is going to be relatively low down here, and then you have other frequencies, which are whole number multiples of that, which will come out to play to give it its sound. The violin, again, has a similar abundancy of that one frequency, but not much in the high end, and the piano and so on. Now, the human ear is a wonder of evolution. It's a wonderful thing. We're able to pick out these individual frequencies within this frequency spectrum, or this range of frequencies. And the human ear can distinguish individual frequencies, but for mathematically it's quite difficult to pick out how much of each frequency is present, and math people and physics people use what's called a fast Fourier transform or Fourier analysis to take these complex waves and break them into individual sine waves. Again, the differences in overtone strength are apparent with these graphs, and again, this is what gives musical instruments their characteristic values. And we use what's called superposition. We're combining all these different waves to come up with funky waves, and more on that now. So let's go forward. This slide's kind of out of place. It should have been at the end of the other one, so we'll come back to that. Skip it for the time being. The interference principle is simply how waves combine to make different waves, and this is called superposition. It's a lot like vector addition. Pluses and pluses will give you big pluses. Minuses and minuses will give you large minuses, and pluses and negatives could give you nothing, 0. So if we look at these two waves and we look at the wave, oh, I don't know, let's look at the amplitude and let's say this is a function of location, or it could be as time goes on. These waves line up. If I draw a line straight down through the entire waveform, so I'll pick a line tool. In this case, and I'll just move it over a little bit so it lines up with points of maximum amplitude. If I have, at that point in time or location, if I have a positive amplitude lining up with another wave that's of positive amplitude, and if they're in phase or in sync, these will give us a large wave. So we could say positive 1 plus positive 1 will give us positive 2. A little wave and a little wave gives us a big wave. Or, like in the next case, negative 1 and negative 1 will give us negative 2. So when these waves combine, the combination of these waves through time and or space, when they're in phase, we'll end up with a larger wave. Let's look at the opposite again. This is called, in this case, constructive interference, to be specifically, or they combine constructively. Now if we come over here and look at this wave, these waves are completely out of phase, in saying that we have a positive amplitude combining with another wave in the same time and or space that has a negative amplitude. This would be positive 1 plus negative 1 gives us nothing. So a wave of 0 amplitude, positive and negative gives us nothing. Or negative and positive, no matter which order you add them in, you get nothing. Or look here, 0 and 0 gives us nothing. Positive and negative, nothing, and so on. So in this wave, we end up with, let's go back up, we end up with no waveforms. This is called destructive interference. Sorry, so sloppy. And lastly, if these waves are out of phase by a little bit, these waves are out of sync by a quarter wave. So this is a quarter wave off of the other one. They will combine, they're partially out of phase. We're going to get not complete constructive interference or destructive. We could say that this is either partially constructive or partially destructive. In the slide they say it's partially destructive, and that's a case of whether the glass is half full or half empty, whichever you prefer. There's partial interference, if you will, and we will have two large waves giving us a moderate size wave because they're slightly out of sync. So let's just imagine we have an experiment where we have two sources of sound. Just call these speakers. Call this speaker A and call this speaker B. If these speakers are emitting the same wavelength or frequency of sound, so you can see the wavelengths are similar, the wavelength crest corresponded with crest, these waves are said to be in phase, and if these waves reach another location, let's say a listener, let's draw a big ear, you get the idea. There's an ear, not a very good ear, but you get the idea. If they reach in phase, we'll end up hearing sound or loud. So waves of positive amplitude combine with waves of positive amplitude to give us waves with even larger amplitude. This is called constructive interference. Now one thing we can do is to move the location of these speakers. So speaker A and speaker B will still be emitting sound of the same wavelength or frequency. I'll just demonstrate that. So I'll go crest to crest here. So that's the distance, that's the wavelength. If I take this and drag it around and go crest to crest there, the wavelength of these guys are the same. So the lambda values are the same. But these waves are traveling with similar speeds, and they have similar wavelengths and have similar frequencies, but they travel different distances. I think we're done with this. We'll get rid of it. These waves, when their sources are separated by a half of a wavelength, will make the waves arrive at a location in a manner that we have a negative amplitude. Just imagine that's the trough of a wave, meeting a positive amplitude, and in this case you get complete destructive interference and you get no sound at that location. Is it possible for there to be sound but there to be no sound? Yes, if the waves arrive completely out of phase. So this is the principle behind noise cancellation. You can buy headphones that will take in ambient noise, outside noise, and flip their phase, flip the sine waves, so you end up canceling as much of that sound as possible. It gives us a richer sound experience. When you go to theaters, in some cases, there are dead spots in the theater because of destructive interference. Let's just say they're the worst seats in the house. Another possibility for destructive interference is not being off by 1/2 of a wavelength, but being off by 1.5 wavelengths, which corresponds with 3/2 of a wavelength. And again, if you look at how these waves will arrive at that location, we end up with a positive amplitude and a negative amplitude. And again, you get no sound at that location. There is sound, but since they're out of phase, they cancel each other. And this person will perceive, again, when they listen with their ear, they'll hear nothing. And that means there are no waves there. You would be standing in a node. Again, another possibility. Hey, let's predict. Let's look at this. These waves are off by a complete wavelength. So I'll draw my wavelength. So there's a wavelength, and if we look at the distance, whoops, sorry about that. Let's just unload that. This distance that these speakers are separated by corresponds with, let's dupe it again, a complete wavelength. So again, here is lambda, the wavelength, and this distance of separation. So I'll draw, let's pick a different color, from center to center. Fix this crooked line. That's better. That distance of separation between these two speakers, if it's off by one wavelength, we'll end up with what kind of interference? You tell me. Constructive or destructive? Think about that. Remember, we have a negative amplitude combining with a negative amplitude. Negative and negative will give me a large wave or a large amplitude that's negative at that point, and it's not loud, or excuse me, it is loud. So to answer my own question, because I'm here by myself, you're going to have constructive interference. Again, if you're off by, how many wavelengths is this? Let's just take a peek. How many wavelengths are we off by? Let's draw the wavelength, and I'll, I don't know, I'll just dupe that. I should select it first. Dupe. So if I drag this over, there's one wavelength worth of separation between the speakers. Let's dupe it again. In this case, oh, how about that? We're off by a distance that corresponds with 2 wavelengths. And again, we have lambda, or excuse me, a negative amplitude meeting a negative amplitude, which will give us a large negative amplitude. Again, constructive interference. Not only can we end up with interference by moving these within the x-axis, we'll end up with interference within the y-axis, and I'll try and demonstrate or try and explain what happens. Where waves line up with each other, let's just say that the waves from the bottom speaker are purple, the waves from the top speaker are light blue. This would be a location of constructive, 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 constructive. So if you walked along that line, you'd hear loud. If you walk along this line, let's just imagine this line carries through, you'd get constructive, constructive, whoops, constructive. Let's get rid of that extra point. Constructive. And just imagine if there were another wave we can extrapolate, there would be constructive there. And because of symmetry, we'll have constructive, 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 constructive. So if I draw lines, if I walk anywhere along these lines, I'll end up with constructive interference. Now, halfway between these, we'll have a crest of the purple wave meeting the trough of the blue wave. Let's just identify the locations of the crests and troughs. So we have crest, trough, crest, trough, crest, trough, crest, trough, crest. You get the idea. Identify the purple waves. Crest, trough, crest, trough, crest, trough, crest, trough, and so on. I'm going to draw locations where the trough of the blue wave meets the crest of the purple wave. So there, there, and there. Here, here, and here. These are locations where you would have a positive amplitude meeting a negative amplitude. So these would be destructive, destructive, and constructive, constructive, constructive. And if we were to walk along, let's take this even farther. So draw as straight line as possible. If I were to walk along that straight line, I'd hear loud, soft, loud, soft, loud. What comes next? Soft, loud, soft. Because I'd be walking through locations where the waves combine constructively to make tall waves and destructively to make no waves. So guess what? You get antinodes, nodes, antinodes, nodes, antinodes, nodes. Let's go forward. Again, here's how it works. These are speakers. We won't see the waves. But again, you get loud, soft, loud, soft, loud, and so on. I'm going to jump online and see if we can bring up an animation or a YouTube of wave interference. Whoops. And hopefully this is going to fit in. I think it will. I think we're going to be in good shape. Perfect. It's going to fit right in our window. And this takes a couple moments. This is old school.
On the surface.
And if we look, we have two
Light
waveforms.
passing through the water is reflected from a mirror through a lens to form an image of ripples on a screen. We've obtained this true image by the Schlieren technique of inserting a stop in the light path. The two small technique of dippers vibrate on the surface of the water. Each dipper produces its own pattern of ripples, and the two sets of patterns overlap. In step, they produce a...
There it is. So this is the wave pattern I was referring to. If you look, I use the pointer. This is the first speaker, or the first dipper. The second speaker, the second dipper. These could be bugs jumping up and down. And because these are each producing their own waves, when these waves combine, we'll get these lines. They're like fingers where the waves cancel waves. These are called nodes. Node, node, and so on. So just imagine you're in this pool of water. If you're sitting on a raft, your raft would hardly move at all because you're in a node. There's no waves moving at that location. If I move over here in the middle, I'd jump up and down quite a bit because it's constructive interference, destructive, no wave motion, constructive, and so on. Our goal in the next video is to be able to identify the locations of these constructive and destructive interferences, and and ultimately what are the rules that determine the spacing between these nodes, or where these nodes or antinodes will fall in space, let's say on that line that we referred to. We'll talk more in a little while.